Hello, this is DVKT Math, and in this video I'm gonna show you how to find the Laplace transform of 1 over 1 plus x. So, well, the Laplace transform of this function is not really common, and the result will be in terms of some non-elementary functions. So, alright, so to find the Laplace transform of 1 over 1 plus x, first notice that Laplace transform of 1 is easy to find, and so Laplace transform of 1, you can write it as Laplace transform of 1 plus x over 1 plus x right here. And then using the linearity of Laplace transform, you can write this as Laplace transform of 1 over 1 plus x plus the Laplace transform of x over 1 plus x, because like in the numerator here we have 1 plus x, so we just separate it out using the linearity of Laplace transform. So Laplace transform of 1 over 1 plus x, which is what we're trying to find, and then plus Laplace transform of x over 1 plus x. And notice that this Laplace transform of x over 1 plus x here is simply x times 1 over 1 plus x. And there's a nice property of Laplace transform for that. So first, well, we let f of s equals the Laplace transform of 1 over 1 plus x, just so that we can simplify the notation a little bit. So here's the definition of Laplace transform. Alright, so Laplace transform of f of x to the variable s is the integral from 0 to infinity of e to the power of negative sx f of x dx. It's kind of like a term twister because like s and x, they're kind of like similar. Anyway, so well, first we need to find the Laplace transform of 1, which is pretty easy using the definition of Laplace transform. So Laplace transform of 1 is simply the integral from 0 to infinity of e to the negative sx times, well, the function f of x here is simply 1, so times 1 dx. So this integral right here is easy to evaluate. It's simply 1 over s. Alright, so it's 1 over s. And then, well, next we're gonna use a property of Laplace transform right here. Alright, so Laplace transform of x to the nth power for any real number n, x to, well, not really any real number n, just integers, because there's the derivative here. We don't want to deal with the fractional derivatives like as much as we can. We just want to avoid that. Anyway, so Laplace transform of x to the nth power times f of x is equal to negative 1 to the nth power times the nth derivative with respect to s of Laplace transform of f of x. Alright, so that's the property that we're gonna use. And so next we're gonna apply that property to this Laplace transform. So Laplace transform of x over 1 plus x. Alright, so x over 1 plus x is x times 1 over 1 plus x. And here our f of x here is 1 over 1 plus x. So it's x times 1 over 1 plus x. It's x to the first power. So it's negative 1 to the first power, which is negative 1. And then times the first derivative. So we have f prime of s here. Alright, because f of s is the Laplace transform of 1 over 1 plus x. And then we just apply this property. Alright, so I'm gonna move to the next slide. So, well, we found the Laplace transform of 1, and we wrote the Laplace transform of x over 1 plus x in terms of f of s, or actually f prime of s. And then we're gonna substitute that into the equation that we got from the beginning. We get this ordinary differential equation. Alright, so this is an ordinary differential equation of, like, in terms of f of s. So we need to solve for f of s, which is the Laplace transform of 1 over 1 plus x, which is what we're finding here. So we get the differential equation f of s minus f prime of s is equal to 1 over s. Alright, and then just multiply both sides, multiply -1 to both sides, we get f prime of s minus f of s is equal to -1 over s. Alright, then, well, solving this differential equation is not that hard. This is a linear first order ordinary differential equation, and well, the integrating factor is simply e. The integrating factor is e to the power of the integral of the coefficient of f of s, and the coefficient of f of s here is just -1, so the integrating factor is mu of s is equal to e to the integral of negative ds, so e to the negative s, and that is the integrating factor. And then multiplying both sides by the integrating factor mu of s, we get this right here. So e to the negative s f prime of s minus e to the negative s f of s is equal to negative e to the negative s over s. Alright, so that is the ordinary differential equation. And then, well, applying the product rule, we can see that this thing right here is simply the derivative of e to the negative s times f of s. That's just the product rule, and actually that's why we need to multiply the integrating factor. That's like the job of the integrating factor, to like turn this into a simple derivative of a product of something times f of s. And so now integrating both sides with respect to s, we get e to the negative s f of s, because integrating a derivative is just getting back to itself. So e to the negative s times f of s is equal to the negative integral. So we're integrating this with respect to s. So negative integral of e to the negative s over s ds. Alright, so this cannot be expressed in terms of any elementary functions. So, well, we need to use the exponential integral. Alright, so the derivative of the exponential integral is this, e to the power of s over s. This is the derivative of exponential integral ei of s. Alright, then applying the chain rule of derivative, the derivative of ei of negative s is, well, just applying the chain rule, we can see that it is going to be equal to e to the negative s over s. Alright, so what can this tell us? Alright, so the derivative of ei of negative s is this. So the integral of this is simply this. I mean, not that whole thing, but this thing right here, ei of negative s. Alright, so I'm gonna go to the next slide. Well, in the next slide, our next job is simply just, use that derivative here, and this is what we get after integrating that and using the exponential integral function. So e to the negative s times f of s is equal to negative of ei of negative s plus c, where c is some arbitrary constant, because we just did the indefinite integral, so we need to have the arbitrary constant c. And so using the definition of Laplace transform, we have f of s, which is the Laplace transform of 1 over 1 plus x, is the integral from 0 to infinity of e to the negative s x over 1 plus x dx. Alright, so from this definition of f of s, we have the condition f of infinity, or the limit as s approaches infinity of f of s is 0, because the limit as s approaches infinity of e to the negative sx is going to be 0, so that whole integral is going to be 0. So using this condition, f of infinity or limit as s approaches infinity of f of s is 0 using that condition, and the fact that the limit as s approaches negative infinity of the exponential integral ei of s is 0. Well, the limit as s approaches negative infinity of ei of s is 0 means that the limit as s approaches infinity of ei of negative s is gonna be 0. Alright, so applying the condition and that limit of the exponential integral, we can, well, f of infinity, the limit at s approaches infinity of f of s is 0. Alright, well, and the limit as s approaches infinity of e to the negative s is also 0. And using this fact right here, limit as s approaches negative infinity of ei of s is 0, which means the limit as s approaches infinity of ei of negative s right here is also 0. So c, the constant c, will be 0. Alright, so we found the constant c using the condition of the initial condition of, well, not really the initial condition, but anyway, using the initial the condition of f of s, we found that c is 0. So this is what we get. So e to the negative s times f of s is equal to the negative of the ei of negative s. And so multiplying e to the s to both sides, we get f of s is equal to the negative of e to the power of s times ei of negative s. So f of s right here is the Laplace transform of 1 over 1 plus x. So here's our final answer for the Laplace transform of 1 over 1 plus x. And it is the negative of e to the s times ei of negative s. Alright. So if you like my video, please like and subscribe to my YouTube channel, and please also follow my Instagram page with the same name, DVKC Math. And thank you for watching.